Hi everybody. We're looking at lesson 2 today, graphs of functions and pre-calc. We're going to look at some common familiar terms first and then explore some new items. So this is a long lesson. You might want to pace yourself as we go along. First, the vertical line test. That's a visual way to check whether a graph of a function is a function itself or whether it's just a relation. And you might recall from Algebra 2, to use that test, you want to think about a vertical line passing across the graph. And if it intersects the graph in no more than one point, then you have a function and it meets the function definition. Let's take this idea, for example. If we have a vertical line and imagine passing that line starting from left to right, just like we read a book, notice that it's only intersecting the graph one point at a time. So that relation is a function. Think about the second one now. Would that be a function or just a relation? And then you can see on the third one that I've got the line drawn here. This one is just a relation. And the same for this one, the circle, it's just a relation. So using that vertical line test, you've done that many times before in Algebra 2. So we'll copy those. The first two are functions, and the second two are just relations. Next, we'll look at intercepts. The x-intercepts are the zeros of the function where the graph crosses the x-axis, and the y-intercepts would be the value when you substitute 0 into the function to find the location where the graph crosses the y-axis. So let's explore that. Here in this graph, we want to look for the intercepts. There's an x-intercept at -3, one at +1, and one at +4. So we have 3 x-intercepts. This would be a cubic function. You can either write them as ordered pairs or as a set. I'm going to write mine as ordered pairs for all 3 zeros of the function. And then the y-intercept, there would just be 1 to be a function, and that happens at -3. So when we know the function and substitute 0 for x, the y value is -3. So x-intercepts and y-intercepts. We did this graphically. Now here's a step where we're going to look at the algebra behind it. Remember, we want to use the rule of 4. And that means representing functions in 4 different methods. In this case, it's algebraically. So I want to take the function and solve that function for when it's equal to 0. And I see in the first 2 terms, if we factor by grouping, I could factor in x squared out of the first 2 terms. And then in the second 2 terms, we could factor out a -4 and still have that common factor of x minus 3. So putting these 2 factors, the x squared and the -4 together, x squared minus 4 times that common factor of x minus 3, then those are going to reveal the roots for us. So x squared minus 4, you can continue to factor or think about the square root method. In this case, we would end up with x is -2 or x is +2, and then our factor x minus 3 would be x is 3. So in that case, we found our 3 x-intercepts. It's a cubic function, so we would expect 3 roots or 3 possible roots. Those are our x-intercepts. And then the y-intercept is just a matter of substituting 0 into the equation. And if you substitute 0 everywhere, we're going to end up with 12 for our y value. So the 0, 12 is our y-intercept. graphically and algebraically, we can solve for intercepts. Okay, let's see what comes next. Next, we're going to talk about increasing and decreasing functions. A function increases in general if you look at the domain and the graph rises from left to right on that interval. And the graph would decreases if you look at the domain and the graph falls from left to right. You notice how I'm thinking about reading graphs like we read a book. Now, it's really important that you pay attention. You're talking about x values, not y values. We're looking for intervals of x values where the y values are going up, going down, or remaining constant. So let's look at a graph here. Well, first I think I have the definition. So here's the definition. If one x is smaller than another x, then the y value is going to be smaller than the other y value. And you can read those for yourself. So here's that statement again. You got to really think about this. We read a graph in math from left to right the same way we read a book. So look at the graph f of x, and we want to trace the interval where the function behavior is increasing using a green pencil. So I could increase, let's see if we can do it with kind of a highlighter maybe, with a green pencil. So the graph is increasing, the y values are increasing there, and they're increasing here. And then decreasing using a red pencil. We'll call that pink. So decreasing is right in there. And then constant using a yellow pencil. So constant would be here. And our directions tell us that we need to identify those intervals. So we're looking at the interval from -8 up to this high point to -4. The function is increasing from -8 to -4, and I've got parentheses around that because nothing's changing at -8, and it starts to change again at -4. It's going to go down. So decreasing from -4 to -2, and then constant from -2 to +3. And then on our last little leg from +3 to 6, we're increasing again. Okay, part D, state the domain of the function. So we'll get rid of all of this shading. The domain of the function are the x values. And in this case, I need to include -8. And we're stopping at 6, but it includes 6. And then the range, the same thing. My range goes from -4 up to +8. -4 to +8. You might notice that I always start with the smallest and end with the largest. Just keeping the order there, just like you read a book, left to right, top to bottom. Okay, oops, excuse me. Sorry about that. Had a phone call. All right, so part F, what thoughts do you have about the intervals that you stated above? Did you use brackets, which meant you closed or included the points? Or did you use parentheses where you had open or non-included points? And why or why not? So you might want to stop the video and record your response. I'm going to record my response and I'll be back with you. Okay, I said something along this line. I use closed brackets for domain and range because the endpoints were included, and I used parentheses for intervals of increase, decrease, and constant because the behavior is changing directions at the beginning of that interval and at the end of the interval. Okay, in example 4, we want to use a graphing utility to determine the open intervals on which the function is increasing, decreasing, or constant. And you can see here on my Inspire that I have the first one graphed, and it looks like it's increasing from negative infinity up to 0, and then it's increasing again from 2 to infinity. Now we could check that with the Analyze feature by using the minimum and maximum. So if I wanted a minimum, I could start here to see that it's decreasing there, and then the same thing with maximum, just to verify that the values were correct. So my function increases from negative infinity to 0, and it also increases from 2 to infinity. You might want to put the union there. The function's decreasing in the middle there between 0 and 2, and nowhere is it constant. Okay, the next graph, let's go turn that one on, delete this one. The next graph has a funny little shape. And the increase begins at 1 to infinity. The decrease is from negative infinity to -2. And the constant is in the middle there between -2 and +1. So intervals of increase and decrease. Let's go look at extreme points now. So we want to look at the idea of a maximum and a minimum. I believe this is my definition here. A local maximum. When the graph of a function is increasing to the left of a point and decreasing to the right of a point, then that point value is going to be the largest value of the function. This y value is called a local maximum. If it's the biggest in the whole interval, it's the absolute maximum. And then a minimum would be just the opposite. When a graph of a function is decreasing to the left and increasing to the right, then that value of f is the smallest, and that would be called a local minimum in that case. And we can explore those ideas here. Okay, so in this example, oh, I lost my pen. In this example, I would say this point F is a local or relative minimum. And D is a local or relative maximum. Point B looks like a minimum. And just for vocabulary, so you understand, you notice how I'm starting here at A, it's a closed point. A's lower than point G, which is an open point here. So G is not included, A is included. There's no more graph. The value at B is the lowest Y value, so I could also call this an absolute minimum on that function, on that domain. It's also a local minimum in this general neighborhood. And you'll notice a lot of times in our textbooks that they drop the words absolute, local, relative, and just call things maximum or minimum. Now here's something to think about. Is there an absolute maximum on this function? Since the y value at A is smaller than the y value at g, and g is an open point there. So no, there is no absolute maximum on this function. There's only a local maximum in that area, and we don't know how big g is, so we can't say g is the maximum since it's not included. And each point right before is going to be a little bit bigger than a. Hurts your brain a little bit. So again, here's another formal definition of local maximum and minimum. And then we've got an example graphically. So based on that definition that we just looked at, the maximum is a y value, and the relative maximum looks like 1. It's the y value, and it happens at 2. So the maximum is 1 when x is 2. The minimum, there's a relative minimum of 0 when x is 4. And there's also a relative minimum of -8 that happens when x is -3. We could also rename this as an absolute minimum on this function. It's the lowest value of the entire function. The range goes from -8 to infinity. It's the absolute minimum. So we've looked at it graphically. Now we want to approximate it with our calculator. I have that graphed here. Let's see. I want to get rid of that one. So turn this one off and go to the third one, turn that one on. Whoop. Turn that one on. So we're looking at the local maximum. Again, I'm going to use that feature, analyze the graph, and look for the maximum. So over here to here, it looks like the maximum is 4.08. And the minimum, to analyze that minimum value, is -2.08 as well. So we have a local maximum of 4 8/100ths. And that happens when x is about -1.15, and the minimum is -2.08, and that happens when x is 1.15. So this graph has symmetry there a little bit on the x values. So right there and right there if you wanted to label those points. So this example, boundedness, this is a new idea. The idea of boundedness is similar to finding extrema. And I look at that graph. The top graph, the first graph is bounded above and below. You notice that you can imagine this is the highest y value and this is the lowest y value. So this would be an upper bound and this would be a lower bound. The function's not going to go beyond that y value or this y value. In this second one, it's only bounded below since the function's end behavior is up on both ends. So this is a lower bound only. Again, this one has an upper bound, and the y values won't go beyond that highest y value. That's the top of the range. And this one is not bounded at all. It goes down forever in the middle here. And then at the extremes up here, it's up around those vertical asymptotes. So not bounded at all. And here's the definitions: a lower bound and an upper bound. A function said to be bounded below if there's some y value less than or equal to every number in the range. and it's bounded above if there's some other y value that's greater than or equal to every number in the range. And if it's got an upper bound and a lower bound, we call that function bounded. Now here we want to talk about symmetry. So in terms of even and odd, we can describe symmetries for graphs of functions. And you might recall the test from Algebra 2. This one test said if you replace x with the opposite of x and you end up with the original function, then you have y-axis symmetry. So this is our algebraic test. We want to do the opposite of x. I'm not saying negative x, because x could be a negative number. We want to read that the opposite of x. And your result is the same y. Then you have y-axis symmetry, an even function like a parabola, y-axis symmetry. And an odd function, your algebraic test is you do the opposite of x, and you get the opposite of y. If that happens, then you have origin symmetry. This one's called rotational symmetry. This one's reflective symmetry. So origin symmetry. Origin symmetry, we're symmetric about a point. That's the origin. Where this is symmetric about a line, the y-axis. That's reflective. Let's give these a try. So can we determine from the graph whether you have an even, an odd, or no symmetry at all? And in this case, I want to be looking, it looks like it's rotational about the origin because, let's see, it looks like 2, -1 is on that graph, and if I replace the x with the opposite of x, -2, +1. So I would say A is an odd function. That's rotational symmetry or origin symmetry. Since it's symmetric about the origin. On B, it's pretty obvious that that's y-axis symmetry. It would be an even function because you can reflect or fold the graph over on that red dotted line and end up with the same points. I see 4, -3 and -4, -3. So I changed the x to the opposite of x and ended up with the same y. So letter B, we have an even function. That's reflective symmetry. It reflected the graph over the y-axis. It's an even function. That's y-axis symmetry. So lots of vocab that we can use to explain, analyze, or talk about a graph. And in this case, I think that looks like neither. How about you? What do you think? Neither odd nor even. Now it does have some rotational symmetry right here around that point, 2, 0, because you see it's just 1 up and 1 down, but it's not even or odd. It's symmetric about the line x equals 2. It's rotated around that point, or 2, 0. It's got rotational symmetry. And you might recall all of those vocabulary words from geometry. Now, how about we can look at even and odd and symmetry from a graph? How about from algebra? So here we want to use the test. You can think about the graph at the same time. So in this case, if we take our test and substitute the opposite of x And the absolute value of a negative number is going to be a positive number. And here you can see I substituted the opposite of x and got the same function out. This is an even function. It has y-axis symmetry. That's called reflective symmetry. The graph, if you think about the graph of the absolute value of x minus 2, it's a V-shaped graph that's been shifted down 2 units. Now x cubed minus 3, we're going to do the same thing. Take the x out, substitute the opposite of x in, and think about the process and the math. If I have a negative number and I cube that, I'm going to end up with a negative value. And this is not the same, and it's not the opposite. So this is neither even nor odd. In fact, the graph x cubed minus 3 would be that serpentine graph, scooted down 3 places, shifted downward. It has rotational symmetry, but that symmetry is about the point 0, negative 3. It's not even and it's not odd. And then finally in letter C, if we substitute the opposite of x in both cases and simplify that, we're going to end up with negative 2x cubed plus x. Now, this function is the exact opposite of what we started with when we did our algebraic test. So this is an odd function. It would have rotational symmetry about the origin. It has origin symmetry. Okay, here's one for you to try. So we want to find all the symmetries, if any, for this graph. X squared plus 2y squared equals 6. Now, you might know this as a conic section from Algebra 2, but if not, we'll just kind of do the test for each one and see what we come up with. So for y-axis symmetry, we want to replace the x and get the same y. And replacing the x with the opposite of x and simplifying that, we're going to get the same y. Everything stayed the same. So yes, we have y-axis symmetry. It passes that test because this stayed the same as the original function. How about, we didn't talk about x-axis symmetry, but we could figure out x-axis symmetry if we kept the x and changed the y. So in that case, if we kept the x and changed the y to the opposite of y, well, we get the same thing. And here, when you square a negative, we're still going to get that positive. So yes, we have y-axis symmetry. They stayed the same. Now, checking for origin symmetry, we're going to change the x and change the y and see what happens there. So we're changing the x to the opposite of x and changing the y to the opposite of y and simplifying. And that stayed the same. So yes, we have origin symmetry. Now there's one more symmetry. That's the symmetry across the line y equals x. And we'll talk about that when we get to inverses, but we could just try that out here. That means I'm going to change the x and the y. So in place of the x squared, we're going to make that a y. And in place of the y squared, we're going to make that an x. And see if we're symmetric across that diagonal line. So does the function stay the same? And that would be, no, this is different. So the graph is not symmetric around that diagonal identity function y equals x. But the graph is symmetric with respect to three different things. There's symmetry, and with respect to the y-axis, the x-axis, and the origin. And if you wanted to solve on your calculator, you would see that this is a elongated ellipse. All right, one more thing to talk about, and that's concavity. So our final thing, concavity and inflection points. Oh my goodness. Sorry about that. An inflection point is where a curve changes from being concave up and concave down, or vice versa. And we need calculus and things called second derivatives to algebraically find that, but we can start to explore those ideas here. You see, at this low point on the graph, I've got a negative slope, and then a positive slope, and then a steeper positive slope, and even more steeper. That function is increasing. The slope is in. Okay, in this next example, you can see starting from the high point, our maximum, I've got a positive slope and then negative slope, and the negative slope is increasing in intensity. So the slope is going down or decreasing. We say this is concave up and this is concave down. So it's got a bump downward and a bump upward. So let's give those a try. If we look at the graph of g of x, we want to determine the intervals of concavity and state where the point of inflection is. So here I've got concave up, and it looks like right there we've changed directions. That's going to be our point of inflection, POI, point of inflection. Then the graph goes concave down, and it looks like right here at 3, 1, I've got another point of inflection, and the graph changes concave up again. So we could write those intervals. Concave up goes from negative infinity to negative 1/2, and then there's a point of inflection at negative 1/2, negative 3. Then the graph is concave downward from negative 1/2 to positive 3, and the point 3, 1 is a point of inflection. And then the graph is concave up from 3 to infinity, because our end behavior is up on both ends. All right, now let's try that algebraically. Like I said earlier, we need calculus to really do this accurately. And if you knew about derivatives, you could calculate this, but we're going to just kind of estimate by taking the average between the high point and the low point, because that would be a good prediction. And it looks like we're 1, 2, 3. So we want to be right in the middle. That would be a half. If I take the average, the x term, average the x terms between negative 2 and 1, cut that in half, our x would be negative 1/2. So if we substitute negative 1/2 into our function here, the f of negative 1/2, 2 times negative 1/2 cubed plus 3 times negative 1/2 squared minus 12 times negative 1/2 minus 4, we're going to find negative 1/8, 3 times a fourth, plus 6 minus 4, and that point of inflection would be negative 1/2, 2.5. The point of inflection is negative 1/2, 2.5. Good luck on the homework. I'll see you next time.